Animation.
PDF map.
You can bin off the sky this week.
Huh?
Just get rid of the sky this week. It's fine. We don't need it.
Technically,
We need the sky.
They also
Can you
take
see
the
from
blank
there?
Yeah.
thing from the...
Well, it's looking.
Here we go.
Yeah. Yeah.
Look away for just a second.
I love them.
Yes.
Are you recording?
Yep, Luke showing off that he's got a memory. He's going to need to stand.
Can you open win instead of double click?
Time now.
Yeah.
You got to hey Dan, we're panopto. Dan, we're panoptoing over here as well.
Yes, you are being recorded.
You need to stand a bit closer, a bit further this way.
You're going to need to
My
be...
favourite astro email ever. What is going on?
Oh, I'm tempted to do this year. It's like 20 pounds. Such a good night here, but it's 20 pounds.
I think you want.
Here we go.
Yeah, I'll do. False guess.
You're going to need to be
Finally.
out from behind
Screen
the
it as
thing.
well.
Make it full screen.
Can you make it full screen?
Control L.
Control L.
Control L.
Oh,
Yeah.
oh.
Cursor.
knows the way around.
Your cursor's on
Oh,
there.
it's gone, it's gone, it's
Scrutinising.
gone. Backseat lecture.
Oh yes, we can set it perfectly now. Might as well take the time to do more now that I've wasted it already. Right, good evening. I am Dan Hunt. I'm a fourth year particle physicist and I like dark matter. It's a confession right there. I'm sure a lot of you do too, to be honest. It's a very interesting thing. I assume it's why most of you are here. There's a better turnout here than most other astro events.
Yeah, all right.
I'm already burning bridges here. Aren't I? So hopefully in today's presentation I'll explain kind of the reasons why we think dark matter exists in the universe, some explanations of what we think dark matter could be, and then some potential experiments that will hopefully discover dark matter once and for all. So we're going to introduce the ideas of dark matter, talk about whether we're the standard model and what leads us to the current design of particle physics, what the current problems are with that standard model of particle physics, and then go into some potential fixes, some quick fixes, as to how we can solve the standard model problem and find dark matter for the first time. So as a quick disclaimer, I'm not a very smart person. I certainly kind of fumbled my way through a lot of software there. I'm neither the best person in the room at particle physics or astrophysics, but I'm going to try my best to explain a little bit of both to you tonight, just to get you a quick insight into a fourth year's perspective on what dark matter is. If you spot anything that's wrong, it's just a test. I'm trying to catch you off guard there. So, as another disclaimer, dark matter isn't a fuel, it's not a TV show, and it wasn't made by aliens. I've heard all three of those be mentioned before somewhere. So to kind of frame the state of physics that's led to us thinking that dark matter might exist, it's worth noting the other times that physicists have found themselves completely and utterly wrong in every way. In the early 1900s, a lot of physicists found themselves completely convinced that physics was done. We were finished. That's it. We can all go home. Everything that's left is just filling in the blanks. Lord Kelvin is arguably on record saying that there's nothing to be discovered in physics now, and that everything left is filling in the blanks. And Max Planck's supervisor, when he went to study his PhD, told him that the majority of his research would just be filling in extra details in his research, rather than, as he did, fundamentally changing quantum mechanics. Oops. But as we know, there's been a long, long history over the last 100 years of physics changing radically, like completely. Starting off in 1905 with the proposal that light could come in little quantized packages, which eventually led to the idea of quantum mechanics. Following on in 1908 to 1913 with the Rutherford experiment, the idea that the atom that we currently know and love, maybe not, is actually a nucleus with an electron orbiting it. Of course, at the time, they didn't know that the nucleus was protons and neutrons. After that, in 1964, Murray Gell-Mann proposed the idea that inside these protons and neutrons were other little things called quarks. You don't need to know much about them for this presentation, but just know that they do exist. In 1969, Binon suggests the idea that some mirror particles may or may not exist, that are the exact same to regular matter, but of the opposing charge, which we now know as antimatter. And in 1983, the superproton synchrotron in Geneva, Switzerland, Cern, discovered the Z and W bosons, which are the carriers of the weak interaction which causes radioactive decays. It's radioactive decays that you've done in GCSE physics. And as you probably know, in 2012, we discovered a little something called the Higgs boson. Kind of a big deal. And that's pretty much the current state of particle physics we're in today. That builds up to the standard model of particle physics. So we have our up and down quarks that are the parts that make up a proton and neutron. These other quarks that don't really matter to us for the sake of this presentation. The force particles, vector bosons, and scalar boson, the Higgs. So we've got the force that keeps the nucleus packaged together, light, the radioactive decay forces, the electron, slightly heavier electrons, and neutrinos, which are required in order to justify a lot of electromagnetic, a lot of weak decays. And we thought they were massless until very recently, when we found out that they weren't. The only ones of these that are particularly going to be worth discussing in particular detail today are going to be the Higgs and the neutrinos. It turns out a lot of dark matter might behave like neutrinos, but that's kind of a spoiler. So it's worth noting that the standard model has a lot of problems with it. Even in the state that it is, there's a lot of problems related to symmetry that we're trying to solve. And in the same way, there's a lot of problems with the universe. Just everything's kind of got problems with it by this point. The main problem, I'm going to talk about in detail today, is that it's a lot heavier than we think it should be. Or at least it was, because we've kind of wisened up to what's going on in the universe now, in strange ways. So I'm going to talk through a couple of pieces of evidence that we have as to how the universe is heavier than we thought it was. The first is one you'll all be familiar with if you've done third year physics observational cosmology. A lot of you won't have yet. This is kind of an insight into that soon enough. And that is the Friedman Equation. The Friedman Equation is a nice, nifty piece of mathematics that basically, if you know the force of gravitational attraction that you've done a little bit of, you can kind of work from a very basic gravity equation and assume that the galaxies are liquid. And from that, you come up with a nice, yeah, that's kind of a reach. That's a long reach there, yeah. Something isotropic homogeneous, everyone's kind of gone through that. And you come from that into the idea that you can model the expansion of the universe with a single equation you can fit on about half a page. And this equation has a factor in it that talks about whether the universe will collapse in on itself at one point, or whether it'll go on forever, or whether it'll just kind of coast, called the curvature of the universe. And it has another factor that's the density of the universe. That one kind of speaks for itself. I don't think I need to explain density too much. So we think that we're in a flat universe. I'll go into the details of why later. It's kind of interesting. And from that, we've kind of concluded that the universe has to have a very specific density so that it doesn't either become too heavy and collapse in on itself, or be too light and expand into infinity. And that's a very specific mass. It's this very specific mass that we don't find if we plug in the regular density of the universe into calculations. Oops. So we know that if the universe is flat, there's some mass that we can't find out there through just looking at regular matter that we haven't found yet. Einstein, chump that he was, introduced a cosmological constant to the equation. He added a constant lambda value that he didn't know what it was. He just thought that there had to be some kind of constant there to justify how the universe is expanding. And then thought he was wrong and took it out. And in 1999, a couple of people came along and proposed that, yeah, the lambda constant should be there in the form of dark energy, which is the other component of the universe that we don't know about, that is not testable. So we're not going to talk about it too much today. That's for the theorists to think about, to deliberate over. Another one that AstroSox members will be quite interested in is galaxy rotation curves. You like galaxies, don't you? A lot. You do. I'm glad at least one person does. So Kepler's law, I'm not going to go into too much detail about what Kepler's law is, but it basically describes the fact that you can find a relation between the mass of an object and its distance from where it's orbiting, and from that find how fast it is orbiting. And this kind of maths can be applied to the rotation of galaxies on the outside. So the further away a part is from the center of a galaxy, the slower it should rotate, because the further away it's got less gravitational attraction to the center. Now, Fritz Zwicky was researching the Coma cluster in 1933, And he found that wasn't the case. There's a lot of people looking at things and finding that everything's completely wrong. It's not us that are wrong, it's the universe. So he found that his models for the universe, as you can see in the plot there, the rotational speed remains pretty much constant, whereas it should decrease, is the specific problem that he found. And he concluded that for this to be the case, there should be 400 times as much dark matter in the universe, or 400 times as much matter, spoilers, in the universe. And that's completely wrong. He's a complete idiot. No, that's not true. But in 1970, Vera Rubin comes along after doing her PhD 20 years before that in galaxy rotations, and looks at the Andromeda galaxy, our nearest neighbor. It's much closer, so it's going to be much easier to observe. And she finds that this has around 7 times the mass that will be needed, which is pretty much spot on these days. Like, our current conclusion is that there is 7 times as much matter in the universe as we can visibly see. So she's completely spot on with that. Unlike Zwicky. The majority of the galaxy is made of stars and hot gas. That's pretty much it. We don't really count into that too much. It's been found that the baryon content in the latter, the hot gas clusters, the regular matter content, is found to be higher than in stars. And we think that this might be because of the fact that these stars are surrounded by cooler gas. This cooler gas not emitting light, so we can't see it. But even if this is the case, these gas clouds that we can find should have collapsed if they're of a higher mass than the stars that we see in the universe. So something must be gravitationally pulling them out so they don't collapse in on themselves. Some sort of halo of some kind of strange matter that's dark. The bullet cluster is one you'll probably all have heard of, at least a little bit, because astronauts do like talking about it every now and again. The bullet cluster is 2 recently collided galaxies that have passed through each other to an extent because of the fact that they have a low density. Most galaxies do in general. Most of the universe does in general. Using the most accurate model of gravity that we have at the moment, general relativity, we can kind of trace back these past clusters in order to work out where the center of mass of this entire system is. And we find when we do that, that the general distribution of mass is outside of the cluster and not inside. This is one of the biggest pieces of evidence that we've got, that there's something out there, not the bullet cluster, that is the most dense part of this system. It's just that we can't see it. Another factor is the mass-to-light ratio. I hope you like the picture. It's the best I could find for this. So the mass-to-light ratio is a factor that a lot of cosmologists use to observe the universe, and it kind of speaks for itself. It's the ratio of an object's mass to how much light it gives out, normally compared with the most well-known bright object, the sun. There's kind of an upper limit to this value, though. If you're looking at a galaxy and you're looking at its mass-to-light ratio, the majority of that light's going to come from stars. Now, stars have to be made, and once they are made, they tend to not be there after a certain length of time. I'll leave that to the astrophysicists to deliberate. And the universe is only 13 billion years old, arguably. So there's only so many stars that could be formed in a particular galaxy. So there's only an upper bound to this mass-to-light ratio. And we've found galaxies above this mass-to-light ratio. Something in there is making it heavier than it should be for those particular galaxies. On the topic of general relativity, you don't need to know too much about it for this presentation again, but one of the main factors that people will throw around about general relativity is the fact that a massive object can bend light, curve light towards it. Now, this can let us see things that are behind a massive object. If the light is curving around it, then you can see objects that you would not normally be able to see. It's one of the best pieces of evidence of general relativity being a thing. It also means we can model this gravitational lensing and see what we should be able to see out in the galaxy if the amount of mass that's there is what we think it is. And we don't. We don't see that. We see a different amount of mass than what we should be expecting. So again, there's some kind of dark matter out there that we can't see. So how do we solve all these problems that we've found so far? We've found so many things that are wrong with astrophysicists. Particle physics hasn't done as much wrong by this point. There are a few problems here and there, but astrophysicists, they've really messed up on this one, haven't they? So, we've changed the way we look at the universe a little bit because of this. They're good at making up for their mistakes, I'll give them that. And they've made a couple of changes known as the LambdaCDM model, CDM standing for cold dark matter, which we'll talk about in a minute. And the LambdaCDM model models the universe pretty accurately to what we see it now. Correct expansion rate, right distribution of galaxies, all that jazz, but it needs two assumptions that we haven't found yet. And it needs dark matter and dark energy. And dark energy. Dark matter being something that doesn't interact with light, or the strong interaction with that doesn't matter too much. And dark energy being some sort of mysterious energy that's making the universe expand at the rate that it is. This constant that was put into the equations of cosmological expansion by Einstein and then taken straight back out like an idiot. That one. But we don't know much about this dark matter, or we'd be talking about it a lot more than we are. Bill Bryson, in his book, A Short History of Nearly Anything, said that for the moment we might as well call them dunnos. Dark, unknown, non-reflective, non-detectable objects somewhere. And that kind of speaks volumes as to what we really know about dark matter. For a start, we don't know whether it's a new particle or whether it's something in space that we haven't found yet. A lot of dark matter researchers tend to categorize dark matter into either baryonic dark matter, which is stuff that we know, and non-baryonic dark matter, which is stuff that we don't. So baryonic dark matter is stuff that we've seen in the universe, but is too dim to see in every instance. Whereas non-baryonic dark matter is an open season. Anyone could make a guess as to what this is, and anyone could be right. That's part of the fun of this. So I'll go over some of the baryonic kinds of dark matter first, because I know you lot do like astrophysics. Black holes. Do I have to explain what a black hole is? I might as well, just in case. Okay, you probably have an idea as to what a dark hole is. You probably know that it's a very massive object that is so massive that it pulls in light itself into it and forms an event horizon. So if anything goes past that event horizon. I'm also sure that any astrophysicist worth their salt would probably call me out on that description as well, and probably will at the end of this talk. So you also might know a little bit about the fact that it is impossible to get any information out of a black hole once it's been sucked in, with an exception, but I'm going to pretend that exception doesn't exist for the moment. So once anything goes into a black hole, it is very, very difficult to find out what it is. So if we have a model of what matter exists in the universe at the very beginning of the universe, and some matter at the beginning of the universe is in these black holes, there's no way for us to have known about it. So there's every chance that this dark matter that we know of is regular matter, but it had formed into one of these black holes before we could actually measure the amount of regular matter in the universe. I hope I explained that. It's a weird one. If the number of primordial black holes in the universe is bigger than we expect it to be, that's a very good justification as to dark matter. That's a good explanation of why dark matter can be seen out there, because it's just a black hole. Another contender, this is one of the big astrophysical contenders, is a macho, standing for massive compact halo objects. It's massive, but it's not quite as massive as the sun, and it's compact because it's smaller than the sun. I don't quite know about the halo. I'm pretty sure they are objects. So the most common example of a macho that we know of is a brown dwarf. A gas cloud that is just under the mass needed to perform any kind of nuclear fusion and emit light, but still compresses into kind of a compact gas cloud. So we find these through gravitational lensing. We found these for the first time through gravitational lensing of something called the Large Magellanic Cloud, the LMC. And we know they can't contribute to all of dark matter, but we know they contribute to some of it. Dark galaxies are another potential contender. And that's just the idea that potentially some galaxies out there have a very low luminosity, a low number of stars in them. Now, it's very hard to find a picture of a galaxy that's very dark. So I instead included a picture of Deep Dark Galaxy from Super Mario Galaxy for the Nintendo Wii. I hope this suffices. I hope everyone's okay with this.
Yeah.
Then we get onto the particle varieties of dark matter. Which one of these is it? I don't know. You know? Please send me an email if you do. We've got masses all over the place here. We've got masses ranging from thousands of times lighter than the lightest thing we ever detected, that we detected by accident, the neutrino, to pretty much the mass of all the dark matter in the universe. So good luck to us. And as you'd expect, there's more and more papers coming out recently that are trying to justify what dark matter could be. And you can see a lot of the potential candidates for what dark matter could be on here as well. Of course, there's a little peek of 2012 with the Higgs. Just saying. So, with all these kind of varieties of dark matter that we've got, it's very important to classify what kind of dark matter people are talking about. So if we start from our regular particle dark matter, you can describe dark matter as either being cold, which is to say that it doesn't travel at the speed of light, or hot, which is to say that it does. Now, we're going to focus mostly on the cold side of dark matter here, with a little bit of emphasis on the hot side, because people who are smarter than I am have concluded that hot dark matter is not the most abundant source of dark matter in the universe, even if it does exist, which it might not, who knows. If we talk about cold matter specifically, we know that if we've not detected it yet, it's either too high a mass to be seen in any of our current colliders and detectors, or it couples too weakly, or it's too unlikely to form in any interaction we've seen so far, and we just need to keep whacking stuff together more to find it. We tend to call those either weak coupling or high mass, low mass. We're going to look specifically at low mass, because if it's high mass, there's every chance that our current colliders can't reach the kind of energies to find it in the first place. So we're much more likely to be able to find lower mass dark matter with some of these experiments. If we look at low mass dark matter, there's either the chance that it interacts only with other dark matter, or if it interacts with normal matter. So it's either self-coupling or an intermediary between dark matter and regular matter. So it could pretty much be anything. But those are kind of good ways of classifying what you're talking about when you say just dark matter. In terms of some of the theory, we're not going to get into a huge amount of it. It's a mess. But one of the major contenders for dark matter is the LSP. You've probably heard of supersymmetry. You probably misunderstood supersymmetry. I know I did. But to keep it simple, supersymmetry is the hypothesis that there could be matter identical to the matter that we know out there, but of a higher mass and with a different spin. We're not even going to get into spin. Spin is too much of a can of worms to talk about in something like this. Some of you will know what spin is. And the thing I like most about the supersymmetry is the names of the particles. So you've got like the sup, down, selectron, skew-on, stow, the neutralino, which is kind of an exception. I don't quite understand that one. So the lightest supersymmetric particle is the lightest of these particles, which is the most likely one to find first because it's the one that doesn't weigh about a kilogram. Other examples on here of potential solutions are the graviton, as you might have seen on the standard model. We haven't been able to model gravity with particle physics yet. That's kind of a bummer. Let's see if we can solve that. The little Higgs, the potential idea that there is a Higgs identical to the regular Higgs, but a little bit lighter. That clue's kind of in the name of that one. Scalar field dark matter, which is to say that there's a field throughout the universe that we can't explain and don't know where it comes from. But it's something dark matter something, and it will have carrier particles that are 10 to the minus 22 electron volts, which, to put it in context, is a million, nearly another million times lighter than the lightest particle we've ever seen. That one's going to be hard to detect. And then there's the idea of fifth dimension, which I'm not even going to get into that. And maybe more. So I'm going to start with some of the ones that we actually could detect and the ones that get referenced a lot in a lot of papers, because we're going to talk about some experiments soon. One of the first ones is dark photons. So if we've got dark matter, we could have a dark force. Ooh. And if we have a dark force, that dark force could have a dark carrier particle. Ooh. So this potential dark force carrier might be called a dark photon. There we go. Pretend that you care at least. This could explain why this particle called the muon has a different magnetic moment, so it spins differently under a magnetic field. And it could mix with regular photons when they carry regular force, and it could be massless and it could not be. But it might exist. That's something. Neutrinos. Now, you might be saying that I've already talked about neutrinos, and I have. But they're by far the least tapped into physics that we actually know about today. Now, you probably know the neutrino from talking about beta decay in secondary school physics. You've probably come across it before from that. Or at least you know that it's something to do with radioactivity, which is about the most you need to know to understand the neutrino here. But it's really light, and it barely interacts with anything, and we've barely seen it. We've never seen a neutrino come from a particle collider. We've only ever seen it in interactions where we are specifically looking for the neutrino with like giant water baths in mountains and stuff like that. It's crazy stuff. So what if we just not analyze the neutrino enough, and there's some kind of physics going on out there that we just aren't aware of right now? So potentially a new neutrino or new properties of the neutrino, anything's possible. There's also the idea of a potential sterile neutrino. I do like the particles. This is a good flush here, a sterile neutrino. A potential particle that just doesn't interact weakly at all and just interacts with gravity. So it would just do nothing. It would just fly through the universe and barely interact with anything whatsoever. Good luck finding that. Axions are another major contender. I couldn't actually find a physical plushie of an axion, but someone drew one in MS Paint, so... Someone put a fair bit of time into it, so I shouldn't be insulting them like that. It's an example of cold dark matter, whereas a neutrino travels at nearly the speed of light, so that's hot dark matter. It's very light. We were saying before about the lightest particle I've ever detected being potentially just under an electron volt, and this is 10 to the minus 12 electron volts, so just over 1,000,000 times the mass of, well, 1,000,000,000,000,000,000 times the mass of the electron, times less than the mass of the electron. That would be a doozy. Up to about 1 mega electron volt, which is about 1,000 times less than the mass of a proton, and double the mass of an electron. So kind of a broad range there, just like everything here. The axion is specifically a theory solution. It solves a bunch of problems related to symmetry that I am not qualified to explain. But the CP, the charge parity problem, is a big problem in particle physics at the moment that some of us are working on solving as part of our master's project. So that's pretty good. Look at new torrents. It also barely couples, just like pretty much everything else I'm going to talk about today. So it's really, really difficult to find because it's barely going to interact with anything. WIMPs are another major contender. Weakly interacting massive particles. Some clever guy came up with this at the same time as the idea of machos and clearly got a promotion because of this. The WIMP is a weakly interacting massive particle, so it interacts mostly through the weak interaction, but barely does it, just like everything else here. It's motivated by supersymmetry, just like pretty much everything else in dark matter. Physicists really like the idea of supersymmetry, even though most of us don't understand it. We're not going to go into supersymmetry again. The mass of the WIMP is somewhere between a GeV, which is about the mass of a proton, up to about 1 TeV, which is 1,000 times the mass of a proton. It's good to put things in context. Under a GeV is going to be called light dark matter, but we're not going to get into that too much ourselves again. And the WIMP is an ideal case for finding dark matter. Most of the other candidates we've discussed so far would be feasible as a candidate if they were with something else, if there was a whole host of other particles out there. But if we find the WIMP, we've got a justification for the problems in the standard model, as well as an explanation of all of the physics problems that we've seen out in space. So we've just done everything in one fell swoop. Well done, WIMP. So far, we've found nothing. We've not found a single thing. We have found what it isn't, though. By doing these experiments in a particular energy range or a particular likelihood of interacting, we know exactly where not to find it. And that's a step. We've managed to whittle down the kind of potential area that we can find any dark matter in. And hopefully, we're getting more and more precise experiments from more and more high-grade technology, and the search continues. As Vera Rubin, one of the researchers I mentioned earlier, a little callback there, said, no observational problem will not be solved by more data, and dark matter is no different. If we keep looking, we're going to find it. Please let us find, please Let us find it. I want to find it. I want a PhD. How do we find dark matter? So I've said all of these things about how it barely interacts with anything, and it's a real bummer because it makes it seem like it's going to be impossible to find. But to put it very simply, we either make it, break it, or shake it. So if we break it, we interact with regular particles that we know about in a way that might produce dark matter. This is kind of what the LHC is doing. The hope is that we collide these protons together and we find something that could be a new particle. For example, the Higgs, when we didn't know that the Higgs for sure existed. We could break it by colliding stuff from space together and finding constituents that come out. The main topic of this presentation, because I don't have to explain things that I don't understand, like QCD and QED, gauge symmetry, I need to know all of those at some point, is shake it. So we're going to be focusing on shake it, the idea that dark matter can interact with regular matter that we know about, and we can see the fact that it has interacted. This is usually for bumping, but we're going to talk about that in a minute. So, I'm going to start on things that you all like. I'm going to start on astrophysics. We're going to look at some telescopes. We're going to go from that into everyone's favorite topic, gravitational waves. Yeah. From that into the main form of shaking, nuclear recoil. Then into the LHC, but not too much. Again, I don't care about it too much in this case either. And then some clever LHC experiments. From that into some particle physics shenanigans, and then just complete inanery. It's going to be fun. So one experiment actually succeeded and has finished by this point. A lot of particle physics experiments have not finished. They kind of get refitted. People don't like wasting money. It's WMAP, the Wilkinson Microwave Anisotropy Probe. This went out into space and measured the cosmic microwave background, which you might have heard of. It's a background radiation in the universe that came from the first moment we could ever see light, 13, 14 billion years ago. So this proved successfully that the universe is flat. Well done us. We know that there's generally an even distribution of energy in this background, so we know that the universe isn't going to collapse in on itself, or it's not going to expand to infinity. At least we're fairly confident on that. Anything could happen at this point. It also confirms the amount of dark matter we see in the universe is what we'd expect. It's a very good experiment to start on because it proves just how wrong we are in our current physics. And it also says that neutrinos, just regular neutrinos, are probably not the form of dark matter that we're expecting. If there were more neutrinos than we think there were, stars would have found it more difficult to clump together at the beginning of the universe. You need to talk to an expert to really understand that. And we would see fewer stars than we actually do. So we know that it's probably not neutrinos. We've stricken one off the list already. 500 to go. AMS is a spectrometer, that is a detector of energy on the side of the International Space Station. It's very high spec stuff. It's got all the parts of the detector that most of you won't care about. So a rich magnet, time of flight detector, silicon tracking, whole shebang. It's got everything. It's really high quality stuff. And it's searching for antimatter in cosmic rays. The idea is that if we find any interactions from antimatter, they could tell us something about either more problems with the standard model, it could pierce more holes in what we already know and ruin our lives even more, or it could tell us something about dark matter, it could find some mysterious candidate that has influenced this antimatter in some way. In general, everyone's going to have a field day looking at all this data that comes out of this. The benefits of this in general is that because it's outside of the atmosphere, we see things that wouldn't reach Earth normally, which is excellent. There's a lot of stuff like that. I'm pretty sure there was a talk on it last year from Paul. It was great. It also goes to really high energies, around 100 tera-electron volts, which is higher than any collider we have today. And there's a lot of potential experiments that could go on because it's being bombarded by literally everything that could potentially hit Earth and then some, which is great. Another experiment going on related to telescopes is CAST, the Cern Axion Solar Telescope. This is a telescope in Geneva, Switzerland that is looking for axions coming in from the sun. Now, I did say before that axions are very hard to detect. So the idea behind this telescope is that were axions to enter it, they would be introduced to a really powerful magnetic field that would then convert these axions into X-rays. And these X-rays are easier to detect if axions become X-rays. Let's see. I did mention gravitational lensing before as well, and this is another useful way of finding the baryonic matter in the universe if dark matter is baryonic. So gravitational microlensing kind of takes advantage of the fact that we found this dark matter in the first place. If a potential baryonic piece of dark matter, like a black hole or a dwarf star, passes past the star, we'll see a slight difference in the amount of light that reaches us, and we'll be able to detect that. And using this, we can work out what the mass of things is that we can't actually see, but we can see influencing things that we can see. And we know that there's actual dark matter out there now. We have actually detected dark matter. We can all go home now. We've found it. We've done. It's at most 20% of all dark matter. That's kind of a shame. The search continues. Another satellite that's going into space is DAMP. It's a satellite launched in 2015. I've not put down the acronym, so I can't remember it. I'm very sorry. It was planned to launch for 3 years in 2015, but it's still out there. Apparently, it's a lot more useful than people thought it was going to be. We're looking for gamma rays, electrons and cosmic ions, anything that is regular matter that could potentially suggest a kind of physics, again, piercing a hole in the standard model or giving us some more information about the mass of dark matter. Looking specifically for WIMPs. See, all the particle stuff that I mentioned before is coming in handy, I promise. I didn't just waste your time. It can handle up to 100 tera-electron volts, which is again higher than any particle collider we've ever had before. So hopefully we'll find something. It's given some interesting results over the 3 years that it was supposed to be launched on regular matter. Not dark matter, but it's getting there. It's still useful, still interesting. And it'll hopefully in the future be able to tell us more about dark matter, because something has to, please. And gravitational waves. You're all here for gravitational waves, right? Not for dark matter. That's what AstroSock's here for. You know about gravitational waves, probably. The idea that in general relativity, space and time are linked, and gravity can affect this space-time so that when two particularly heavy bodies interact, you can see kind of ripples in the space-time. You can actually physically detect and prove that general relativity is a real thing. And Birmingham did a discovery a couple of years ago, and everyone patted themselves on the back for it, and it was great. It was a good time. So it causes all objects to oscillate in the universe because space-time itself is moving. So if something that we don't know is there affects the kind of oscillations, we'll be able to see a difference in the gravitational waves that we detect. Again, this is something that's fairly speculative at the moment. People are more talking about the idea of doing this rather than actually doing it right now. But we can compare modeled gravitational waves to gravitational waves that we see in reality to identify the kind of things that we can't actually visibly see in the universe and potentially find more data about dark matter. It all comes back to dark matter eventually. I hope so. So now on to a couple of the experiments out there that are a bit more particle physics oriented, kind of going into nuclear physics. So I mentioned the idea of shaking before, breaking, shaking, making. And one of the particular ways to investigate shaking is nuclear recoil. So the idea that dark matter, because it's got mass, can bump into things, and those things will move. And if they move, we know that something has hit them. And if we can't find the thing that hit them, it might be dark matter. So NewsG is an experiment in Birmingham right now that stands for New Experiments with Spheres Gas. One of the acronyms that actually makes sense. You're going to see some horrible acronyms later. Trust me. Particle physics is the best for terrible acronyms. We love them. So NewsG is specifically looking for axions and WIMPs, kind of low mass dark matter that does interact weakly, but mostly looking at the mass. And it gets detections, it gets signals that specific to a particular kind of matter. And the general goal of the experiment is that if we see a particular signal that doesn't match any kind of matter we've seen before, it's dark matter. And that makes it a very simple experiment. There's no fiddly bits going on. It's also a very easy to detect it because it's as spherical as it is. It's very simple, and you can change it all the time. You can change whatever gas is going. I worked in it over the summer. It was a great time. Now you might be wondering, how does it work? I'm going to show you how it works. So here's our NewsG experiment. We've got a positive charge in the very center, and the rest of it is filled with a gas. Now along comes a particle from space, and approaches our detector, and it enters. As it enters, it whacks into one of these atoms, it hits a nucleus, and this nucleus recoils. When it recoils, it's given a bit of energy, a little packet of energy, a quanta of energy. And this quanta of energy ionizes it. So now we've got a positive ion and an electron that's just been let out. And this electron is going to be attracted to the positive charge in the middle. So it's going to move towards it. As it moves towards it, it's being given more energy because it's closer to the positive charge. So more electrons get formed. It whacks into more ions. More electrons get made, and you get an electron avalanche, it's called. So now you've got more electrons, all of which are heading towards this positive charge, this anode in the center, and produce the signal that we see. Now, the amount of energy, the mass of the original particle will change how much it bounces, which changes how much energy the electron comes out has, which changes how many electrons it will make, which changes how quickly it reaches the detector. And all of that can be used to identify what whacked the gas. I'm a man of scientific terms here, what can I say? Don't worry, there'll be more animations later. And this will be examined. LZ is a similar experiment. I'm not going to go too much into the scientific details because I don't want to be bored just as much as you don't. But it's a combination of two other experiments called Lux and Zeppelin 3, which managed to reduce the constraints of dark matter by doing things very similar to the News G experiment that I showed you just a second ago, except with liquid. And instead of electrons coming out, they see photons, a process called scintillation. Now, Zeppelin 3 placed particular limits, as did Lux, and then the two combined to make the LZ detector. You can see a chamber of liquid in the middle, a lot of shielding to stop anything that isn't dark matter from going in, and then the same thing would happen. Dark matter would come in, it would produce photons inside, and these photons would be detected by a bunch of photon multiplier tubes on the outside. Now, we've not got any particular results from this just yet, but recently, a similar experiment known as Xenon 1P found an example of the rarest decay possible to be seen ever. Xenon 124, which has a half-life, so half of any sample of it will decay, in 10 to the 22 years. So this decay has happened once, and we know exactly where it happened, when it happened, and what angle the radiation came out at. So to say that this experiment is accurate, or that experiments like this are accurate, is an understatement. Let's see if we can find dark matter with it. A couple of similar detectors, not to go into too much detail, are DEEP, which stands for Dark Matter Experiment with Argon Pulse Discrimination. These acronyms get worse, I promise. DEEP is an experiment for the same collaboration as NewsG, SNOLAB, and I've not got too much to say about it, apart from that detector looks very cool, and I wanted to include the picture in the presentation, and I couldn't find anywhere else to put it apart from here. CDMS stands for Cold Dark Matter Search. It works with a solid rather than a liquid, and when it's hit by dark matter, it produces heat, a little vibration. And this vibration travels through the material in the form of what physicists like to call a phonon. I'm very sorry, people who are doing quantum approach to solids, or have done quantum approach to solids, to bring up the phonon. You can repress it now, I promise. Ice Cube is a very similar experiment to LZ, except instead of using liquid, it uses a kilometre squared of ice in Antarctica. Now, any experiment that is in Antarctica is very cool. So I have to bring it up, and there'll be another Antarctic experiment coming up later, I promise. This will come in relevant. Gamma. I'm going to see it on here, actually. Investigations on particle dark matter. Highly radio pure scintillators. The worst acronym you'll see. I love it. That's the only reason it's on here, really, apart from the fact that it's looking with these really pure scintillators, silicon scintillators this time, doesn't matter too much, and that's looking at galactic halos, so the very outside of a lot of galaxies that we think could contain large amounts of dark matter. So it's looking at those with incredible sensitivity, and it might have found some evidence of dark matter. It's found oscillations inside it of around 2 kilo electron volts, so really, really tiny. That's like, it's 100 times less than the mass of an electron. But it's there, and it could be dark matter. The only problem is that by making it a really accurate scintillator, we've stopped it from being able to identify what caused that pulse. So we know that something might be dark matter, but we don't know if it is. It could just be regular matter. The search continues. I have to bring up the LHC. I'm very sorry to the astrophysicists out there, but we're going to go a little bit more into particle physics by this point. Not too much, don't worry. Not too many details. I'd be called out if I gave details because I would get them wrong. Atlas, the experiment that discovered the Higgs boson, the very big one, the one that the University of Birmingham is very proud of for the most part, is looking for contenders for the lightest supersymmetric particle. So it's whacking protons together and seeing if something gets spat out is dark matter. It's also looking for it's got lots of irons in the fire. The benefit of the Atlas experiment is that it's capable of pretty much finding anything as long as you can be bothered to look at the huge amount of data that it makes. LHCb, which stands for LHC Beauty, is doing the exact same thing, but it's also looking for very particular constraints on a lot of the charge parity problems I mentioned earlier. This is in the hopes that we can get constraints on what dark matter could potentially be, if it was to be a solution to these problems, which it also might not be because we don't know what dark matter is. The LHC is too complicated to talk about in something like this, and it's going to get very messy if I do. So we're going to focus on some of the smaller particle physics experiments like we kind of have already, and talk about some of those in more detail. Two exceptions to that rule are Phaser and Codex PD. Now, Phaser is looking for particularly long-lived particles like HCOs, dark photons, light scalar matter, pretty much everything that's quite light and goes for a very long time, as well as the first detection of collider neutrinos, because like I said, we've never seen neutrinos if we weren't explicitly looking for them before, and it would be really nice to do that. It's very cheap, only $1 million. That's chump change in the particle physics industry. It's about 2 meters long. It might be extended to 5 meters if it finds anything good. And it's made from Atlas and LHCb modules, so it's pretty much held together by shoelaces, this thing, in the context of particle physics. The first paper for this thing was made in 2017, and data taking begins in 2021. Now, for context, the majority of these experiments are proposed 20 years before they're actually put in place. So for this thing to have been proposed, be accepted, and have the components accepted and traveled and constructed and set up and have PhD students set up ready to analyze this data in just 4 years is kind of ridiculous. You might want to know how it works. So, in the LHC, protons collide with each other. You probably know that much. They interact, they produce some extra particles, and these particles, because the center of mass of the entire system is completely zero, are going to be produced perpendicular to the beam. Because you've all done this in physics, I assume. You should throw them 2 trolleys towards each other, and they'll either bounce off in the opposite direction or they'll stay still. It's kind of the same, but also not. But it's probably the best way of explaining it. So these things travel off perpendicular. And all of the Atlas detectors, I should add, are designed to detect this stuff that travels off completely at a right angle. But what if this dark matter is very light? If this dark matter is very light, there's every chance that it wouldn't travel perpendicular, it would travel along the beam. And it's just passed by every single detector that we have, every single way of finding dark matter, every single way of finding anything, and we've just lost our one opportunity to find it. If only we had some kind of detector completely perpendicular to the beam, waiting there for any matter that just travels completely along the beam line and travels 500 meters, say, from that. So it's a good thing that we have Phaser, which is exactly in that place. Very convenient. I should mention that Codex PD is a very similar experiment designed for a compact detector for exotics LHCb. I couldn't find the acronym for Phaser. It's a very similar experiment for LHCb, but since LHCb goes for physics that is going mostly forwards, it looks for matter that's coming off at right angles, kind of the opposite situation. So a simulation for that is in Birmingham. The 2 people who I know who regularly go to AstroSoc meetings who are involved in Codex B aren't here today. So I can just say whatever I want and they'll not call me out for it. For more particle shenanigans, we can look at Pico and drift. Now, Pico is a combination of 2 collaborations called Picasso and Coupe. You ready for these? You ready for these acronyms? We have project in Canada to search for SUSY objects, SUSY being supersymmetry, and Chicago Observatory for Underground Particle Physics. And it's a collaboration of those two experiments together. It hopes to use what's known as a bubble chamber to search for dark matter. Now, a bubble chamber is very old. If you know what a bubble chamber is, you probably also know that there's a reason we don't use them anymore, and it's because they're just not capable of the accuracy that we need to find most relevant physics today. The idea behind a bubble chamber is that we have a liquid, and when a potential matter particle comes through, we compress the liquid, so it gets into a very strange state we call metastable. This particle will then travel through this liquid and form a little bubble of gas. It heats it up just a little bit, so a little bit of it reacts. We then expand the chamber so this bubble becomes much larger to the point where we can detect it. That's the idea, at least. For any modern day experiments, we have to be compressing and expanding it way too fast for it to ever be relevant. But the Pico collaboration hopes to be able to use this technology on a smaller scale and much more at a speed that's kind of capable of being used to detect dark matter. Always good. The current detectors for Pico are 2 litres and 40 litres. The 2 litre has shown some very promising results and some very accurate readings, and the 40 litre is about to show some results in the next couple of weeks. So let's see. A similar experiment in North Yorkshire, no less. The directional recoil identification from tracks. This uses another piece of particle physics technology called a time projection chamber. Now, to not go into too many specifics about what a time projection chamber is, imagine that you've got a chamber of gas, a charge inside this, and then particles are passing through this chamber that has a magnetic field in it because it's got this little charged layer. Now, these particles are going to travel through this chamber in different ways depending on how heavy they are and what charge they have. And because of that, these particles will travel through in different ways, which it can then detect. That's the general idea. We can detect a particle's charge and kind of its mass and the momentum it had when it was traveling through. So hopefully that's interesting. Let's see. I didn't look into these in as much detail. And finally, final experiment, don't worry, we're almost done. GAPS, the General Antiparticle Spectrometer. This is a hot air balloon in Antarctica looking for anti-deuterons, which is an anti-proton and an anti-neutron. Remember when I mentioned dark matter earlier? It's all coming together. I planned this perfectly. From space. So we're looking, we've got 1,440 lithium detectors in a layer of 10 layers of 12 by 12. And it's on a gondola. It's the only particle physics experiment I know that contains a gondola. This gondola, of course, not being a gondola, but being a weight that helps the detector stay stable while it's in a hot air balloon, which is in Antarctica. This is still strange. If only we had a way of finding out how this works. So this is our detector. It's in Antarctica. It's in a hot air balloon. And it's got these silicon sensors here that are capable of detecting light. But dark matter might not be light. How do we deal with that, I hear you ask? So, this dark matter comes in from space. He's here again. There's some kind of interaction that may or may not produce deuterons, but if it doesn't, this experiment will not be able to find them. So it produces deuterons. These deuterons travel into the detector, and many of these deuterons will hopefully travel into the detector over time. GAS hopes to be able to take many of these deuterons, mash them together, make them into a really unstable nucleus, which is really unstable, and because it's so unstable, immediately decays into a bunch of X-rays of really, really high energy. And the hope is that by taking this particle that we didn't know anything about and having it decay specifically into deuterons which specifically form these photons, we'll be able to detect these photons with the technology that we currently have, even though they're at very high energy. So those are all the experiments I could talk about today, but I've got a couple of honorable mentions. A couple of honorable mentions go to the FCC, ADMX, Macro, the Gaia Galaxy, Ani, Xenon, Fermi, Hawk, Veritas, Camel, Multi-Dark, CDEX, Dark Side Hawk, Clean, Crest, Pure, Palais, Every LHC Experiment, Cogent, Saber, Magic, Edelweiss, DMTPC, Cosine, and Pandex. This is experiments looking at dark matter. So dark matter is a very interesting experiment research, and it's getting stranger by the year. Any one of these experiments, and any one of the ones that I listed, or any that I couldn't find under Google search, could be the experiment that finds the missing link. So keep that in mind. And remember, the real dark matter is the friends we made along the way. Thank you.
How long did it take you to make the animations?
Longer than I'd care to admit. I don't know. PowerPoint is very good for animating, actually. You'd be surprised.
What was the name of the Antarctica experiment again?
The
I want to know it's and learn about.
Yes, this one, right?
Yeah.
General antiparticle spectrometer.
I know, I'm curious.
I mean, that's kind of the idea, get people interested in all of the dark matter experiments that are out there.